Hello, my name is Jim Schall, and I am an instructor for Federal Highway Administration training delivered under the National Highway Institute. The National Highway Institute, or NHI, is the training branch of the Federal Highway Administration. The videos you're about to watch are based on some of the training courses developed by the National Highway Institute, in particular, the Introduction to Highway Hydraulics course, NHI course 135065, and the Culvert Design course, NHI course 135056. I've been an instructor for National Highway Institute training courses for 25 years. I completed my undergraduate engineering degree at Purdue University and did my master's and PhD at Colorado State. The videos are based on demonstrations and experiments that we do primarily in these two training courses, built around a portable flume. The flume is 6 inches wide and approximately 5 feet long and recirculates water from a 30-gallon sump. The videos, there are 6 of them to watch. The recommended order in which to watch those videos: first, open channel flow concepts, then grate inlets, culvert hydraulic concepts, hydraulic effects of culvert liners, aquatic organism passage design concepts, and energy dissipators for culverts. Thank you for your interest in Federal Highway Administration training. I hope you find this video series helpful in completing highway drainage design projects. This video will demonstrate the hydraulic performance of a number of energy dissipators appropriate for culvert applications. We'll be looking at how the energy dissipator operates, the fluid number range it's good for, and we'll be evaluating the exit velocity from the energy dissipator using our pitot tube. First thing to note is that typically we don't need energy dissipators on an outlet controlled culvert. In outlet control, we typically don't get the high velocity conditions. Remembering our culvert hydraulics and outlet control, we're typically subcritical. We could be full pipe, lower velocities, lower slopes. We usually don't have high energy dissipation requirements. In contrast, in inlet control, when we're flowing supercritical on a steep slope, coming out of the end of the barrel at high velocity, there's often a need for energy dissipation. And what we're talking about are things more than the normal riprap apron that's often used downstream of many culverts in a highway related project. Before we get into the actual energy dissipators, I want to spend a few minutes reviewing hydraulic jumps, because some of the energy dissipators are based on hydraulic jump theory. Most of the energy dissipators we're going to look at are from other sources. They weren't developed for culvert application. They've been researched and developed over the years for typically reservoir applications, and that's where particularly a hydraulic jump energy dissipator is often used, some form of a hydraulic jump energy dissipator. Federal Highways has collected the energy dissipators that might have application in culvert design and put them in a publication, Hydraulic Engineering Circular number 14, the hydraulic design of energy dissipators for culverts. So that's the source where a lot of this information comes from. We'll start looking at hydraulic jumps, and then we'll jump, if you will, right into the energy dissipator models that I have laid out on the table. So let me turn on the flume, and we'll look at what I like to call a traditional or a strong hydraulic jump, a textbook style, if you will, hydraulic jump. The strength of a hydraulic jump and the characteristics of a hydraulic jump are a function of the incoming fluid number. If you remember from your basic fluids, the fluid number, FR, equals the velocity divided by the square root of GY. The larger the fluid number, incoming fluid number, the better the hydraulic jump you will have. So this is a pretty classic textbook style hydraulic jump where we're coming from supercritical flow, high velocity, supercritical flow, and in my flume I can get to about a fluid number of 3 to 3.5. We don't typically get a really good hydraulic jump with significant energy dissipation until we get above, say, a crude number of 4. So I've got something close here. This type of jump, or any hydraulic jump for that matter, will depend on the downstream tailwater condition as well as the incoming crude number. Many people think that the hydraulic jump creates the downstream tailwater, where we go from this supercritical flow to a more tranquil subcritical flow. But in reality, it's the opposite. If I don't have the tailwater, I won't get the jump. And the reason is because hydraulic jump is basically an application of the momentum theory, which says I have to have some kind of force to counterbalance this incoming momentum from this high velocity, high crude number condition. And if I don't have that force, I can't make that force balance work. As a, for instance, if I change the tailwater even a little bit, you can see this jump move downstream. If I put the tailwater back in, there's enough force to counterbalance that incoming momentum and to make this hydraulic jump form. So this is, like I say, a classic hydraulic jump. But hydraulic jumps come in all different shapes and sizes. There's one jump at the other end of the extreme that we call an undulating jump, where we don't get this well-formed hydraulic jump. I'm going to change the discharge and change the flow conditions a little bit to create an undular hydraulic jump. So I'm going to start to increase the slope again till I get my supercritical flow, but it's going to be a very low supercritical flow, something in the range of just over 1, maybe 1.1, 1.2, in that range. And you'll actually be able to see this jump start to move downstream. So this wave front that's forming right here is in fact a hydraulic jump. We're going from our supercritical to a subcritical flow, but because we don't have a good strong approach crude number, we don't get a real well-defined jump. That's why we call it an undular jump. I remember when I was doing my master's degree work, I was in the lab trying to set up a flow condition, and I had this kind of wavy surface that you see downstream that's pretty typical of an undular jump. And I couldn't figure out why I had that or how to get rid of it. So I went to my major professor and said, "Can you come look at the flume? I'm not sure what's going on." He comes out to the lab, looks at the flume, basically says, "Oh, you have a hydraulic jump," turns around and walks away. And I'm going, wait a minute, I know what a hydraulic jump looks like. It's that textbook style one I just showed you at the beginning of the demonstration. It's not this sort of thing. But in fact, he was right, because we're going from a supercritical, but a low supercritical number, 1 to 1.5 into the 2 range maybe, where we don't get a well-formed jump. We still need the tailwater to make it happen, because if I take the tailwater out, the jump will sweep downstream, and we'll have supercritical flow the entire length of the channel. Which brings us to the concept of hydraulic jump energy dissipators. We'll be looking at those. One of the more common ones are the depressed style basins that are actually buried into the ground. You see these around reservoir projects, in order to get that tailwater, to make sure, to kind of guarantee we have a tailwater condition adequate to counterbalance that incoming momentum. Before we do that, let's start looking at some of the other types of energy dissipators. I've got a model here that I'll use that allows me to insert different energy dissipators. Depending on whether it's a structure that's low or a structure that's high, we'll only be using one of these barrels at a time. So I'll start with the low elevation structures. Let me increase the slope a little bit to get to a nice supercritical flow. We'll measure the velocity coming out of my barrel here once it is well established. So you can see in this lower barrel we have supercritical flow, part full pipe, supercritical flow conditions. I'll take my pitot tube and I put some rubber bands on it here so I can monitor the initial elevation of the velocity head, v squared over 2g. So it's in this range here. And what will happen now is we'll start looking at some of the energy dissipators. The first one is called roughness rings or tumbling flow, depending on how the structure operates. This is an internal energy dissipator. It's not attached to the end of the barrel. It's actually part of the barrel. And in fact, it's only for the end of the barrel with 5 rings, 1, 2, 3, 4, 5 rings that slow the water down inside the barrel. It does require sometimes that you oversize the barrel at the outlet in order to accommodate the roughness rings, but it's a very efficient, cost-effective energy dissipator that works well for a lot of applications. It doesn't require additional right-of-way. We end up with a pretty significant velocity reduction. We're about half of what we were before on our pitot tube. It's a very cost-effective structure. We've used these several times on different projects, storm drain projects as well, with outlet structures where you have high velocity flow. Culverts, again with high velocity. And again, if you're in inlet control, you've got this supercritical part full flow condition, so you often have enough barrel to accommodate the roughness rings even without oversizing. But if it's really high velocity flow, you will end up oversizing the barrel as the model shows. So the tumbling flow energy dissipator, it's a very effective, cost-efficient structure that works quite well. If we go to some of the external type structures, the first one we'll look at is something we do a lot of in highway drainage design, rock riprap. Now, quite often we'll have an apron right at the end of a culvert that might extend 25, 30 feet. What many people don't realize is that there is actually a Federal Highway Administration design standard for a rock riprap energy dissipator. This was developed by the laboratory at Colorado State University in conjunction with the Wyoming Highway Department. It actually has a depressed section in the riprap. It has an insill made of rock. I can't make it flare according to the design standard because my flume is a constant 6 inches wide. But it dissipates energy by both roughness of the rock riprap, by the plunging that is created in the plunge pool, and by the insill, which is where I'll measure the velocity. And again, like the tumbling rings, we've cut the velocity head in half from where we started. So this is a pretty effective energy dissipator as well. One way to think about this is it's not much different than if you had a scour hole develop at the outlet of a culvert, and instead of going back in and refilling the scour hole and then putting a rock apron on it, put a rock lining into the scour hole, and you've kind of effectively created a very similar type of energy dissipator where you have a plunge pool condition that helps dissipate the energy. So rock riprap energy dissipator, this one's, you know, of course, described in Hydraulic Engineering Circular number 14. The next class of energy dissipators we'll look at are energy dissipators that are based on primarily impact forces. So there's usually some kind of blocks or baffles at the outlet of the structure that cause the energy dissipation to occur by impact force. This one's called the Contra Costa, developed by the Contra Costa County folks to primarily be applied to irrigation canals in California. It consists of a low baffle and a high baffle. We should have some tail water on this one to make it perform a little better. And with the tail water, you see we get a fairly effective energy dissipator, again with a velocity head that's about half of where we started. With the water impacting the first baffle, going over the top and around the side, impacting the taller second baffle. These energy dissipators are all built to scale, so the length of this is proportionally correct when we compare it to, for example, the next one we'll look at, which is the hook energy dissipator, which is quite a bit shorter. So the Contra Costa, it's good for Froude numbers. All of these type that are on grade are typically lower Froude number range, less than 3 for most of them, beyond which they're not nearly as effective. The hook energy dissipator, designed around 3 hooks that are placed in the channel downstream, was originally designed for a pipe arch application, but it's been used since then for a variety of other culverts. It is a very compact, very short structure. The model study tests on this one were done at the University of California, Berkeley. And again, if we look at the exit velocity, it's really quite tranquil. You see how the flow impacts these hooks and spins around a little bit. You see a little bit of a rooster tail coming up here. One thing to be aware of on any of these energy dissipators, and particularly the hook, is you want to follow the design standards that are outlined in Hydraulic Engineering Circular 14 very closely. This is one case where it really doesn't pay to get too creative as an engineer, because all of these energy dissipators were model study tested to make sure they work. We've seen applications where they tried to use just a single hook in the middle of the channel, and the water came out and hit that hook and flew to the sides and went out of the channel. So follow the design standards. It does take 3 hooks to make this perform effectively. It is very compact, but again limited in Froude number to something less than 3. Perhaps one of my favorite small culvert energy dissipators is a USB-R Type 6, sometimes known as a hanging baffle, because it is literally a hanging baffle in front of the culvert outlet. It's a very compact energy dissipator as well. It handles Froude numbers up to 7, so it has a higher Froude number range than many of these other at-grade type structures. It operates by impact and redirection of flow. At lower flows, it's the impact force on the hanging baffle, the water plunging under the baffle. At higher flows, the water gets spun around and overtops the baffle and exits out. Doesn't require tail water to work properly. It's self-cleaning, so even if you see one of these with sediment that's filled in between floods, it will flush that sediment. And it too is hydraulically very efficient, provides a very tranquil flow release at the outlet of the energy dissipator. So the USB-R Type 6, a very good structure. The reason it's for smaller barrels, which in the highway environment can be a fairly large structure. This is only good to a discharge of 400 CFS. Anything larger, it's unknown as to how its performance will be. Now we're going to move into some of the hydraulic jump type energy dissipators. We have 2 of those to look at. The first one is an at-grade hydraulic jump energy dissipator. It's called the CSU energy dissipator. It's based on having some roughness elements downstream of the outlet of the barrel The number of rows, the spacing on the rows, the height of the elements is all defined by the design criteria. And it too provides very effective energy dissipation. It's limited in frood number compared to any of the depressed hydraulic jump basins, which we'll look at next. But it's a very simple design concept. It's fairly easy to build. It can be flared or rectangular in geometry. One concern with this is, and we see this again, some folks try to get creative, some engineers, and they look at this type of energy dissipator and they say, oh yeah, well that's easy enough to do. We can put some roughness elements on the channel, the apron downstream of the culvert, but the spacing, the size, even the distance downstream from the roughness element is critical in how that energy dissipator will perform. Trying to, say, put roughness elements on a standard end section on a small barrel causes more trouble than what it solves, because the roughness elements are so close to the exit of the barrel, flow hits them and starts flying up in all different directions. So follow the design standards and it'll work as you expect. If you do something different, it's unpredictable. Okay, so this is one of the category of depressed hydraulic jump energy dissipators. And in order to show this one, I have to shift my flow to the upper barrel. And the way this would actually work in the real world is this basin is depressed into the ground. If you go to a reservoir and you look at that stilling basin at the outlet of a large reservoir, it'll be some type of depressed structure. This is called the St. Anthony Falls. It was model study tested at the University of Minnesota, St. Anthony Falls Hydraulic Laboratory. And it's a very effective hydraulic jump energy dissipator. It handles frood numbers up to 17, which is quite an increase from where we were, simply because we have this guaranteed tailwater by depressing it into the channel. Let me get a little more tailwater so it looks like it should in the real world. There we go. And again, as you can see, the exit velocity is knocked down to little to none as we get out into that more tranquil subcritical flow after the hydraulic jump. The idea of these types of stilling basins is to force the hydraulic jump to occur in a specific location by using roughness elements and end sills, thereby ensuring that the jump occurs in the structure. The flow that's leaving is very tranquil, it's subcritical, will not damage the downstream channel. These types of structures would only be used in a culvert application on very large culverts, maybe culverts in very highly erodible soil. It's not as common as some of the other energy dissipators that we use. And in fact, any of these structures, of course, add cost to your project. So if there's any way to reduce the need for energy dissipation in how you design the culvert, that would be the first step. And one way we can do that, if we remember our culvert hydraulics, is that in inlet control, which is where we typically need this energy dissipation, the roughness of the barrel will not change the headwater. So if we designed a culvert as an RCP and we have high exit velocity and it's an inlet control, we could change the pipe material to CMP if there weren't other overriding issues. That roughness would help slow the velocity down and might eliminate the need for an energy dissipator. The other part of this then is to think about energy dissipator design as an integral part of your culvert design. Don't design the culvert and then all of a sudden think, oh, look at that, we have high velocity, I better design an energy dissipator. Because again, these are expensive structures and you might be able to avoid it or minimize the size of structure needed. The last one we'll look at is kind of a special type of structure. It's called a stilling well. Sometimes it's called a bubbler because it redirects flow. It might be used on a down drain from a highway project, for example, down to the Toa Slope channel. Idaho DOT used a number of these on a steep downgrade to bring water off the highway down to the valley below, a series of these 3 in a row. The water comes into this, is redirected upward, and tends to literally bubble out of the structure and then continue on down the channel. Some concern for debris trapping, particularly for coarser sediments. It will flush fine material. Some concern for freezing in a winter climate. So a lot of them will have say a 4-inch PVC pipe to drain the low flows out of the stilling basin, stilling well itself. But as you can see, again, a very effective energy dissipator that has application in highway drainage design. So that's an overview of some of the hydraulic characteristics of energy dissipators that might be suitable for culvert applications. These standards are all reviewed in Hydraulic Engineering Circular number 14. You can also design these energy dissipators using the Federal Highway software, culvert design software, HY8. It has a module that allows you to design an energy dissipator, which is fairly unique to that software program. There are other culvert design software packages available, but the Federal Highway HY8 is the only software program that does the energy dissipator design. So you can design your culvert and then jump straight into the energy dissipator module, transferring that culvert information and look at different options for your energy dissipator. If you have any additional questions, refer to Hydraulic Engineering Circular number 14 or the accompanying training course in the culvert design course, NHI course 135056. We go through energy dissipator design and show these models as well. Thank you for your interest in Federal Highway Administration training. I hope you found this video series on energy dissipators helpful.